Good morning everybody. I am Dr. S.V. Uma, working as Associate Professor in the Department of ECE, RNSIT. I will be continuing from Module 4 in Basic Electronics, which includes Part 1 includes flip-flops, and the prescribed textbook for this is textbook 2, which is Kothari and Nagrath. And the units what you need to study is as mentioned 12.1, 12.3 to 12.5, and the part 2 of this module includes microcontrollers, which we only discuss the most basic structure, just the introduction and architecture of what are microcontrollers and where we use them. And the prescribed textbook, it's one of your reference books, that is Mazidi. It's Muhammad Ali Mazidi is the author. Microcontroller and Embedded Systems 8051 is the name of the textbook as shown. So let's see what are the objectives today. So first thing is, what are flip-flops we should try to understand and why we use them, and the basics of flip-flops, that is latches. What is a latch, what is a flip-flop, what are the differences and where we use them. The second thing is to understand the working of an SR flip-flop or RS flip-flop to draw its logic diagram, truth table and timing diagram. You've already seen what is a logic diagram, what is truth table and all that. You've seen the realization of basic gates. So we would continue with that, use a part of it here. So let's see what are flip-flops. We already know that logic circuits can be divided into two types. That is, the first one is combinational logic circuit and the second one is sequential logic circuit. So what do we mean by combinational logic circuit? Combinational logic circuit means the current outputs depend only on the present value of the inputs. We don't need any memory in this circuit, and it doesn't depend on any enable or clock input. So no need of enable, no need of clock, and no need of past inputs or outputs, no memory. So give a set of inputs, you will get a set of outputs as shown. So here x1 to xn can be a group of inputs and z1 to zm can be a group of outputs from this circuit. So this circuit can include a set of basic gates, AND gates, XOR, XNOR, whatever, all kind of gates. This is a combinational logic circuit. So we've studied many such circuits. The examples what you have studied are half adder and full adder, subtractors, decoders, multiplexers, code converter circuits and so many more. So these are some of the example applications of combinational logic circuits. And one thing what you should remember in these circuits is the propagation delay in this circuit depends only on whatever is the delay involved in the logic gates. That means each of in this structure we have lots of logic gates put to form some particular logic. So whatever logic gate is put, the total delay of the circuit will be the delay involved in passing through the different stages of logic gates. Stage 1 may be AND gates, stage 2 may be OR gates, so on. It's a sum of products expression you are realizing. Then you will have two stages, one stage of AND gates, one stage of OR gates, and whatever is the delay involved in each AND gate and OR gate, one AND gate, one OR gate will be the total propagation delay involved from passing of the input to the output side. So it is quite small. Now we will see what are sequential logic circuits. Sequential logic circuits, in opposition to combinational logic circuits, depend on the present as well as past sequence of inputs. So it depends on the past inputs also and the past outputs also sometimes, and it along with the present category of inputs. And so now what should happen in a sequential logic circuit? It should be able to remember or store the past history of the inputs so that it will be able to produce the current output. So what was the previous input? It has to remember. It has to remember what was the previous input or the input before that, maybe 2 or 3 stages before what was the input, and based on that it will generate the current output. That means we have to have some kind of memory incorporated in the circuit, and we call a set of signals at any particular point. So, we choose different points in a circuit, and the value of the signals at those particular points are called as a state. We will call it as a current state, next state, previous state, and so on. We name it like that. So, all such circuits are normally called as finite state machines, or FSMs in short. So, finite state machines are also sequential logic circuits because they depend on current as well as past inputs. So, memory is incorporated in this circuit. Now, along with that, usually a clock is needed for synchronization. We can have both asynchronous and synchronous forms of the circuit, but usually we need a clock also for synchronization. And just remember this, the key to build memory or the key to build storage in the circuits is by using feedback. So, if you use feedback in your combinational logic circuit, you will be able to incorporate memory into the circuit. Let us see how a sequential logic. As you can see in this sequential logic circuit, it is nothing but a simple combinational logic circuit which depends on present inputs x1, xn, generates a set of outputs z1 to zn, and along with that it also generates y1 to yr, a set of outputs. This is taken and fed back to the input side, so that the logic here incorporated here depends on the present inputs, the present values of x1 to xn, and the previous output values y1 to yr. So, here it depends on the present as well as previous values. Here it is depending on the previous output values. This is the way we can incorporate feedback. So, a memory element is shown here through which the feedback signals pass through. And in this circuit we should remember the propagation delay which we spoke of here depends on the circuit which we have here, that is the combinational logic circuit, and it also depends on a clock frequency. We are going to connect a clock signal to this circuit also. So, once you connect a clock signal, that clock frequency will also matter in the computation of the propagation delay. How much delay is taken in generating output given a particular input. So, the examples for the sequential logic circuits are flip-flops, registers and counters. These are some of the commonly used sequential logic circuits. There are two types of sequential logic circuits. The first set we call as synchronous sequential logic circuits. So, synchronous sequential logic circuits are those which are controlled by one master clock. So, there is one particular master clock which has control on the complete operation of the circuit. That means all inputs are sampled at that particular edge of the clock signal. So, one rising edge or falling edge of the clock signal, the inputs are sampled and the output is taken at that particular time. So, timing will be fixed in these circuits and as controlled by this master clock. As shown here, inputs are sampled at specific clock intervals and therefore, the state as well as outputs will change only at those clock intervals. It can be edge of the clock, okay, either rising edge or falling edge of a clock normally. The other type of sequential logic circuits are asynchronous sequential logic circuits. In this asynchronous sequential logic circuits, we do not have any master clock or clock pulses, or many of the times no enable signal also. So, output responds immediately to change in the input values. So, whenever the input changes, the output is going to change. So, this kind of circuits are called asynchronous circuits. So, there is no synchronism or matching with one particular edge of the clock. Generally, what are the clock signals we use? We normally use square waves for clock signals. you use waves like this. So, square waves are normally used, and at the rising edge the inputs are sampled, maybe the input A which is high and input B. So, input A was high, input B can be low, this is 1, this is 0. These values are considered at this particular clock edge. So, at one particular clock edge, if you consider the values of inputs, and the output will change at this particular time. So, if A is high and B is 0, maybe the output should remain in 0 state. This is the output. If output should remain in 0 state, it is taking the sample exactly at this clock interval. What happens? The values of inputs are taken and the output changes state. It remains in 0 state. So, this is how it works. Excuse me. Yeah. So, we saw the types of sequential circuits. Let us move on to the next thing, latches and flip-flops. So, what is a latch? What is a flip-flop? What is the common difference between the two? So, the most popular varieties of storage cells or memory cells used to build sequential circuits. They are called the basic building blocks of sequential logic circuits, and they are latches and flip-flops. So, what is the difference between both? A latch is nothing but a level sensitive storage element. That is, it senses a level, either a high or a low. So, it senses whether the output is in high or low, and it detects the levels and works according to levels, whereas the flip-flop is edge triggered storage element. So, usually the clock edges which I spoke of in the previous slide, positive or negative edge, that detects the it's a flip-flop. So, in a flip-flop edge triggering is used, whereas in a latch level triggering. So, if I give an enable signal only when the enable signal is high, the circuit behaves as it is designed. If at all the enable signal is low, the circuit will not work. That is how a latch works, whereas a flip-flop uses a square like clock signal, and at every edges there will be a change detected. So, this is the common difference between a latch and a flip-flop. So, common examples of latches, we study SR latches, S bar R bar latches, so complemented input latches, D latch and so on, gated D latch, etc. And common examples of flip-flops, the D flip-flop or the delay flip-flop, sometimes also known as data flip-flop, and D flip-flop with an enable input. Then we have the JK flip-flop, the toggle flip-flop, T flip-flop and so on. These are the common types of latches and flip-flops used. Next, let us see how to build this latch or a flip-flop. So, the basic element which is needed to design a latch or a flip-flop is called a bistable multivibrator or a bistable element. As the name indicates, a bistable is one which has two stable states. One is the high state, the other is the 0 state. So, a bistable circuit always has both stable states. When do you say a state is stable? A state is called a stable state if it is going to permanently remain in that state unless and until there is an external trigger to make it change its state. So, you need to maintain it at that particular state until you give an external trigger to help it change the state. So, such a circuit is called a bistable multivibrator or a bistable element, and using two simple NOT gates, we cross couple those NOT gates as shown in this figure to form such a bistable element. This bistable element is capable of storing one bit of data, or it is a memory element. We can see how this works, how it is capable of storing one bit of data, we can easily see here. And we say the upper NOT gate output is connected to the input of the lower NOT gate, and vice versa. Output of the lower NOT gate is coming to the input. This A and B just specify some current values. On power on, it can take any values. So as soon as we don't connect exclusively any inputs here, you can see no separate input is given, it is just cross coupled, output of one to the input of the next, and so on. So they are two cross coupled NOT gates, and we can see how this works. On power on, if at all we assume that this A is 1, if this A is 1, so A is high, then what happens? This Q will become 0. If at all A is high, Q becomes 0, and if Q is 0, this 0 is coupled to the next stage, and what happens to Q bar? Q bar remains high. So you can see the permanent state of the output, Q will be 0 and Q bar will be 1. Output will permanently remain in this state, and hence this is called as one of the stable states of the multivibrator. So it is one of the stable states, 0 and 1 state. And one more thing what you should notice, there are two states in the output. We have complementary outputs available. You have Q as well as Q complement or Q bar. This can be called Q bar, or it can be indicated as Q dash. So complementary outputs are available in this element. So I can say now this cross coupled NOT gates is capable of storing one bit of data, that is 0 at this condition. Okay, it is storing one bit of data. In the next state, we can see what happens when there is a on power on, if at all A starts with 1. So on power on, if we have 1 here, then what happens? Q becomes 0, and this 0 is coming here, Q bar becomes 1, and the next state is this with A 0, with A 0, on power on A starts off with 0, then A bar is nothing but this position Q, that is what I have called A bar here. This A bar will become 1, and whenever this becomes 1, the same value is coming to this B, and this becomes, Q bar becomes 0. So I have a 1 here, then Q bar becomes 0. So you can see now the permanent state of this bistable element, it will have Q as 1 and Q bar as 0. So this is the second stable state possible for the bistable multivibrator. So the first stable state was when Q was 0 and Q bar was 1. And the second stable state is when Q is 1 and Q bar is 0. So in this case, I can say this is a memory element which can store 1 as its data. So it is storing 1 in this case. The complemented form of that is also available or stored. So this is the second possible state, and we get both these states without giving any exclusive inputs. On power on, any A or B can take any one of the values depending on the circuit. So it could have any of the values, and depending on the values, the output will either store a 0 or a 1, and its complemented form also. So this hence works like a basic memory element. And there is a third case possible, which is called the metastable state. What is this metastable state? Metastable state is the state when both outputs are midway between zeros and ones. So when the outputs are halfway, it it has gone above 0 but it is still below 1, then it is somewhere halfway through the change, and this is known as metastable state, and it remains in that state for a small duration of time. So, it is midway between 0 and 1. So, what in summary, what is a bistable element? A bistable element will always have storage of a binary symbol in a form known as state. So, it stores a binary symbol known as state, and it normally has two stable states. So, one is when q is high and q bar is low, the other one is when q is low and q bar is high. So, generally we depend on q. Q is the value stored. Q can be either 0 or 1. So, it can store one bit of information, and the process of storing a 1 is called setting the element or setting the latch, and the process of storing a 0 is called resetting the latch. So, whenever q is 1, we say the latch is set or the bistable element is in set state. Whenever it is 0, we say the bistable element is in reset state. And as I have told you before, there are no inputs given to the basic bistable element. It assumes any value for A and B, and on power on it just assumes some value and continues. So, however, it is possible to give inputs in two different ways. So, next we will design a latch, an extension of this basic element. So, the bistable multivibrator is the fundamental element which is used to make a latch and then a flip-flop. So, now we are going to extend the concept of this bistable element and see how the inputs can be added to this element. So, I can add inputs in two ways, either asynchronously or directly, and the other way is synchronous inputs. So, when I add asynchronous inputs, it means irrespective of the enable or clock signal, those inputs will change the outputs. So, the inputs affect the outputs without any clock signal affecting it, and synchronous inputs are those which will not cause a change in the output immediately, but it will cause a change in the output only during the positive edge or the negative edge of the clock. So, either at the rising edge or falling edge of the clock, the samples of the input signals are going to be taken and the output will be computed. Till then, if it is not in those edges, somewhere in between, the output will not be computed till the next edge of the clock signal comes. So, we say it happens in synchronism with the clock, in correct timing, matching timing with the clock. That is how you can give synchronous inputs. So, now let us come to the basic definition of what is a latch. A latch is a class of flip-flop whose output responds immediately to appropriate changes in the input in spite of the presence of an enable or clock signal. So, let there be an enable signal, let there be an additional input called as clock signal. In spite of all that, the output will change as soon as the input changes. It won't wait for the clock or enable signal. That means we are asynchronously giving the input in a latch. So, it is a class of flip-flops where output responds immediately to change in the input signals. It does not bother about clock or enable. You can see the basic example of a NAND gate latch, also known as the S bar R bar latch. So, here we are taking complemented inputs, that is why the name S bar R bar. So, this is an S bar R bar latch. As you can see, in this circuit you have S is the actual input here, S bar is created here, and R is the input, R bar is created here, and you have cross coupled NAND gates N1 and N2. So, these cross coupled NAND gates means output of one gate is fed as input to the other, output of N2 is fed as one of the inputs to N1. So, this is how it is going to work. So, the same thing is shown in the second stage also. Only thing what we are showing here is for one particular condition of inputs. So, here also I have directly considered S bar and R bar. So, we already have S bar and R bar present here. Okay. So, this is S bar and R bar. You can directly look at this NAND gate and we will analyze how it is going to work. Its working is similar to that of the bistable element using cross coupled NOT gates what we saw. You will see a similar operation here. So, the first condition what we are going to consider is when this input is 0 and R bar is also 0. So, when both inputs are 0, do you remember the operation of a NAND gate? In a NAND gate, if any one input is 0, the output will go to high state. Please remember, NAND is not of AND. So, 0 and anything is 0, not operation of 0, not 0 means it is 1. So, any single output, it can be a multi-input NAND gate, even if a single input goes to 0 state, the output will permanently go to high state. So, for this NAND gate, let me call it N1. For N1, the output is high because S bar input is 0 and R bar input is also 0 for NAND gate N2. So, the output of this gate will also be high. Sorry. So, here if this input, if one of the inputs is 0, the output will remain in high state. So, now what is happening? Outputs of both the gates are logic high, which means they are not complements of each other. Ideally, what did we see in a bistable element? One output Q should be the complement of Q bar. If I have 1 at Q, I should have 0 at Q bar. That is how it is going to work. We needed complemented outputs, but in this case, when both inputs, we are adding inputs to the bistable element here using NAND gates. So, when both inputs are 0, the outputs are both becoming high. Hence, we call this as an indeterminate state or a forbidden state. So, this state is not allowed for an S bar R bar latch. This state, when both outputs are permanently high, you can see it in the truth table. So, Q and Q bar are both going to remain high. This is a not allowed state, or it should not be used in this condition. So, both inputs being 0 is not permitted. Next condition, let us see. So, if S bar is 0, then what would be the output of N1? The N1 output will surely be high, and R bar we are choosing. So, this condition S bar is 0, R bar is 1. So, R bar is 1 and S bar is 0. So, for 0 input, output is permanently in high state, and this 1 comes as the input to the second gate N2. So, for the second gate, both inputs are logic high. 2 inputs at one state, 1 and 1 is 1, not of that is 0. So, output Q bar will come to low state, Q is in high state. So, this is called set condition because Q output is logic high and Q bar output is 0. Output Q is what we are interested in, it is in set state. So, we call this function as set state when Q becomes logic 1. Okay. So, this is how it works. Now, the third condition, let us assume, that is when S is high and sorry, it is not getting selected, its selection hogtilla. Okay. Okay. So, the third condition here is S is high or S bar is high and R bar is 0. The third condition in this truth table, when S is high or S bar is high and R bar is 0. So, now first look at the lower NAND gate. N2 output will go off to one state because one of its inputs is 0. You always have to see which input is 0. If one of its inputs is low, output of this gate will be high permanently. Now, this one is fed back to the first AND gate N1 whose other input is 1. So, 1 and 1 is 1 and therefore, Q becomes 0. So, now the output Q which matters is in 0 state, which is also called as reset state, Q0, Q bar 1. So, this is known as reset state for the flip flop, and here we say this memory element or latch is storing a 0. In the set state, the latch is storing a 1. And finally, now the last condition is when both are 1. That means S bar is also high, R bar is also high. Now, how do we determine the output? Let me assume Q bar is the other input to this gate. So, Q bar and 1 is Q bar itself and not Q bar here would be Q. So, now I would get Q as the output. That means its previous value, whatever I had before, the same value continues to remain now. So, I will call the previous state or no change state. Similarly, this Q is coupled to the input of the second gate. So, Q into 1 or Q and 1 is Q and complement of that because it is a NAND gate. So, Q complement, that means again the same state. So, the output remains as Q and Q bar and this is called as the no change state or the same state. So, output remains in the previous state. We also call this as previous state or no change state or same state. So, this is how a simple NAND gate S bar R bar latch works. So, just remember, only if both inputs are 0, then both outputs will go to one state, which is a forbidden or it is a indeterminate state for a NAND gate latch. So, only that state should not be used. If S bar is 0 and R bar is 1, then the output will be set, Q is high. If S bar is 1 and R bar is 0, remember we have complemented inputs. That is why when S bar is 0, output is high, and when S bar is 1, output is low. And when both are high, then it remains in the previous state or the same state as before, no change state it is called. You can see the logical representation of this flip flop. The symbol can be with complemented or bubbled inputs for S and R because I am supposed to get S bar and R bar. So, since I am supposed to get S bar and R bar, we have bubbled inputs. It can also be shown like this, S bar and R bar bubbled inputs, and both the outputs here are shown as Q itself, but a complement or bubble is added in the second case to show that the actual output here is Q bar, whereas this is Q. Okay. So, these are the logical symbols or representations for the S bar R bar latch. Now, the important points about this, always remember outputs Q and Q bar are complementary to each other. The circuit will always have two stable states. One is the set state when Q is high, the other is the reset state when Q is 0. So, since it can remain in these states and store one bit of information, whatever is the value of Q, we can call it as a 1-bit memory cell. This S bar R bar latch what we have studied is also called as 1-bit memory cell, and what we have done now is an asynchronous latch because there is no clock signal or enable signal, output changes in response to the inputs immediately. So it's an asynchronous latch. Next, let's see a NOR gate latch. A NOR gate latch is very similar to a NAND gate latch, only we are using cross coupled NOR gates instead of NAND gates. So we have two cross coupled NOR gates here instead of NAND gates, and you can see one more change here. We have direct inputs R in the upper gate and S in the lower gate. Previously we had complemented inputs. For a NAND gate latch, we had S bar and R bar. S bar was given to the upper gate, R bar to the lower gate. The change here is R is nothing but reset input and S is the set input. R is given to the upper gate and S is given to the lower gate in this case. So this is the main change. We can analyze the working very fast. So if both are 0, what happens? If this is 0, then the other input to this NOR gate will be Q bar. So Q bar or 0 is what? Q bar itself, and complement of that, it is not OR, NOR gate. So the final output remains as Q itself or Q double complement, and similarly here S is also 0. The other input coming to this is Q, and therefore Q or 0 is Q itself, and we have complement of that bubble, therefore Q bar. So what happens? The output remains in same state as before or no change state. So here when R and S are both zeros, there is no change in the output. So please remember, two zeros for R and S, no change in the output. The second condition is when this is when R is 0, or let us say R is 1, S is 0. So this is just S and R, that bar should not be there, okay, a small correction. So here R is 1 and S is 0. What happens? In a NOR gate, if any one of the inputs is tied to logic 1, the output will go to low state, because 1 or anything is 1 itself, not of that is 0. So please remember, just like in NAND gate, if one of the inputs was 0, output would permanently remain as 1. Here, if one of the inputs is tied to logic 1, output will permanently remain as 0. So for this gate, output is 0, and for the second gate, both inputs are zeros. So 0 or 0 is 0 itself, not of that is 1. So the output here will be Q is 0, Q bar is 1. This is called as reset state. So Q is reset to 0. Similarly, the next state, R is 0 and S is 1. This is called set state. So what happens in this? This gate B's output will be tied to 0, because one of its inputs was in 1 state. So since this is 1, you can directly say output of this gate will go off to 0, property of NOR gate. Now if this is 0, the output of this gate Q becomes high. So Q is high and Q bar is low, which is the set state, the third condition in the truth table. And finally, we have the last state when both are high. If both gates are tied to logic high, outputs of both NOR gates will be tied to logic low. So if any one of the inputs is high, output will be 0. So remember, we need to have complemented outputs. If Q is 0, Q bar should be 1. That's not the case here when both inputs are at high. So this forms the indeterminate state or the forbidden state, as I told you, which is both 0 state in this case. For NAND latch, both high was the forbidden state. Here both outputs are becoming low in a NOR gate latch, and the logic symbolic representation for SR latch using NOR gates, S and R direct inputs, Q and Q complement. We have a bubbled output shown here. So, this is how it is represented. So, this is how it works. So, next let us see what is an RS flip flop. An RS flip flop is just an extension of this latch, the NAND latch which we used. So, you can see the same NAND gate latch here as we have shown before, but I have two more NAND gates connected as inverters. The idea behind that is, whenever set input is high, I want to make, so whenever set is high, output Q should be high. Whenever reset is high, I want Q to be made 0. So, to achieve this condition, see here, set state is when S is high, Q should be high. What did I get in an actual NAND latch initially? We used complemented inputs, S bar and R bar. So, whenever S bar was low, then output would be high. So, to get a direct match, when I say set input should be high, output should be high, and whenever reset is high, R is high, Q should be 0. So, you add two additional inverters here. So, what happens? This S, if it is 1, this becomes 0. So, actually I am giving S bar itself here. This part works similar to the S bar R bar latch what we have studied before. Only thing is I am complementing the inputs beforehand. So, the truth table here changes slightly. The 0 0 state for S and R is the no change state. The working is exactly similar, only I am giving inverted inputs initially. So, when S is 0 and R is 1, whenever reset is 1, the output should go to 0 state. The Q should be reset or 0. That is all I am achieving here. So, whenever R is 1, output of this gate becomes 0. You can see this gate output becomes 0, and whenever this gate output becomes 0, Q bar will be high. If Q bar is high, Q will be low. That means output is in low state, and this is achieved whenever reset was high. Similarly, whenever set input was high, the third case, whenever set input is high, the output becomes high. That means when S is high here, this becomes 0. So, output of this gate becomes high, or Q is high. So, Q becomes high as normal. The other things work as normal as we have analyzed in the other cases. The only additional thing what I am achieving here, when S is high, I am getting Q as high. When R is high, I am getting Q as low. So, reset is given, the output should become reset or 0. When set input is given as high, output should be in set state or 1 state. So, for that we are just adding two more NAND gates to invert. That is all. Now, let us see what are gated flip flops. RS flip flops are said to be transparent or gated if any change in R or S is immediately transmitted to the outputs Q and Q bar. So, gated flip flops are those where a clock signal is used to change the output. So, a clock or enable signal is needed here. The most common clock signal is a square wave. As I have already told, the most common clock signal is a square wave. Let us just see finally what is a clocked RS flip flop. So, you can see in this case the additional input is the clock input C. This clock is the additional input. We have the same circuit as before. The RS flip flop what we studied, it is the same circuit with S and R as input. So, what happens when there is a clock? Only when clock is high, as well as whenever the clock is high, the output of this gate is enabled to take whatever is S. So, I will get C into S whole bar, clock into S bar as the output of this gate, and clock into R bar as the output of this gate. So, clock only high value for C enables these two NAND gates. If there is a 0 here, whatever is given in S or R, that would not be shown at the output. The output will not change depending on SR or R values. Only for clock to be high, S and R values will be reflected at the output, and this latch behaves exactly similar to what we have analyzed, the basic S bar R bar latch. So, whenever clock is low, output of both NAND gates is, output of this NAND gate is also 1, output of this NAND gate is also 1, and this latch, so if it is 1, this latch will be disabled. Okay. So, please remember that. Okay. So, in a clocked RS flip flop, the final truth table what we need to analyze is for S and R, a simple NAND RS flip flop, the truth table is as shown. You have a clock signal here, the bigger one you can see. The clock signal is shown, this CK, and only when the clock is high, the first 4 conditions, only when the clock is high, the truth table will be same as in the previous cases. So, whatever truth table we got, SR00 no change state, 01 is the reset state, 10 is the set state, and 11 is the forbidden state. So, we got the same response as in the previous case when clock is high or enabled. If at all the clock is 0, then irrespective of S and R, the output will remain in the no change state or the previous state. That means the complete flip flop or latch is disabled. So, output will always remain in the previous state or the no change state. So, inputs respond only in synchronism with an enable or clock signal. This is what is a clocked RS flip flop. So, in summary, what we learnt throughout this chapter, this is all you have in your syllabus for latches and flip flops. We learned to differentiate between what is combinational and sequential logic circuits. Combinational doesn't need a master clock. Output, present outputs depend only on previous, depends only on present inputs and no need of clock. In sequential, a clock is needed, memory is needed, and present output depends on present as well as previous inputs and outputs. So, memory is there in sequential, no memory in combinational. We learnt what is the difference between a latch and a flip flop. Latch works with either no clock and enable or just a level sensitive enable signal, whereas a flip flop works with edge sensitive clock, either positive or negative edged. Then we analyzed in detail an S bar R bar NAND latch, a NOR latch, as well as an RS flip flop, clocked and gated flip flop. You can have a set of questions in this topic as shown, like what's a flip flop, explain its working, what's a latch, explain either a NAND or NOR latch using a truth table, and with the help of a truth table you analyze and show. How does a sequential circuit differ from combinational, and so on. So, why universal gates are normally preferred in flip flops. So, these are the general kind of questions. If you have any doubts, you are always welcome to ask. So, let me wind up this class with this set of questions. Thank you.